Right. Right. So good morning, everyone. And we'd like to start off our first day with inviting Professor Aryan Kaushik from University of Sussex. So he's with the University of Sussex since 2021, I believe, and he has been the invited panel member for the ICT EPSRC's ICT prioritization panel in 2023. And the list goes on. He has over 75 keynote talks all across the globe on different IEEE and Elsevier conferences that take place, as well as he's on the editor list for those as well. A few to name are the top conferences: ICC, GlobeCom, VTC Spring 2023-24, WCNC, and so on. So I think it's best we invite Professor Kaushik to give a talk. And the title of his talk is Integrated Sensing and Communications, a Tale of 6G Innovation Beyond just communication. So there's more to expect beyond communications. Thank you.
Thank you. Thank you, Prof, and Ramon as well for the invitation. And I'm glad to be here. And thank you so much for attending my talk today. So, no, it's fine. Yeah, I think I have to be closer, right? I hope you can hear me. So, that's fine. Does this work or?
It has been unplugged. So don't.
No?
Our camera will stop working.
Okay, so I'll try. So the topic of my talk today would be on integrated sensing and communication. So my group has been working on it for a while, and I would like to present some sort of latest updates and some, the sort of roadmap that we have aligned with 6G, or sort of INP 2030 framework that we have. So all sorts of things you will see. And I've also given a couple of links. I don't know if we're going to provide the slides later, but if you feel free to go to any of these links and sort of open for collaborations and like queues or anything like open for. So basically, just a quick thing about me. So I'm actually joining as associate professor in Manchester, so this is a bit of news. And I've been with the University of Sussex, as Prof mentioned earlier. And before that, I was with UCL, University of Edinburgh, and a couple of other unis as well. And I've been involved quite a lot in sort of the PhD thesis examination, the editorships, and several of these things. I was also PI for a couple of projects and sort of co-PI as well, researcher too, just to name a few here. And I was also fortunate enough to be visiting professor or researcher at a couple of institutes around the globe. So mainly, I think you see from Asia and Europe, but yeah, I was around for a while. And also, I've been involved quite a lot with ComSoc and sort of IEEE activities in several of these things. I'm also one of their online content board members, and also basically chair of one of the ETIs that is upcoming now, electromagnetic signal and information theory. So just very quick thing about me. So basically getting into the topic. So as you can see that what we were actually expecting from the several 5G sort of services, right? So we were working towards the sort of triangular framework, right? Where we had this enhanced mobile broadband, ultra reliable low latency communication, and basically massive machine type communication, right? So to provide very massive connectivity. So if you look at this sort of triangle here, so this was our goal when we thought about the IMT 2020 sort of standards, right? And basically you see that the 5G subscriptions are only increasing, right? So we see that compared to the previous standard, let's say LTE or 4G, and if you want to go even further. So we see that the 5G subscriptions by 2029 are expected to reach some number, which is here about 5.6 billion, which is a good number, right? Which is a big number. Because we see that we are evolving. So one fun fact here is that we promised a lot of things in 5G, but we did not really fulfill all of these, right? So we're still working on these. And we are also trying to advance our 5G infrastructure with 5.5G. You see that many countries don't even have 5G. So depending on what you really want to play around with it, you come up with either 5G or 5.5. the idea of 5.5G is to really advance the same triangular framework that we have with our three main key usage scenarios and work towards these and improve these, right? That's basically the idea of 5.5G. And you see that the subscriptions of for 5G, one population coverage that we have is just going to increase, right? If you see around all the industry reports and so on. So just a quick touch upon on what we were expecting with 5G. But you see that with 6G, a lot of things change, right? When 6G framework comes into picture, which has been recently adopted by the TUR, you can see that a lot of things change here, right? So here, you're not just working on the triangular framework anymore, you're actually adding up some enhanced capabilities, right? So you have your immersive communication, you have your massive connectivity with your any you try to achieve the hyper reliability, low latency communications. This is there, so you keep improving it because the idea is you do not want to change too many things in your infrastructure. Rather, you want to complement these with some additional things. So we come up with three additional enhanced capabilities. So first one is the multifunctionality of our systems and networks. So what I mean by the multifunctionality is that integrating different systems and different networks, different operations, different functionalities together. Right? So first one is the star of the show, one of the stars, is integrated sensing and communication, basically combining sensing and communication together. So these were, let's say, two different operations. So let's say if your sensing equipment was operating, let's say, 2 gigahertz or 3 gigahertz, and your communication, your mobile device was operating, let's say, 4 gigahertz. You don't need to use two different frequencies. You can have the same frequency, right? And you can also implement them on the same hardware, right? To save the resources, to have the cost efficiency. You can also have them coexisting under one network, really depending on your application. So let's say I can have my radar sensor at the back of this, room at the corner. I can have my mobile device here. They can coordinate with each other and to provide this sort of multifunctional output together. In terms of monitoring the environment, also communicating the information, right? Or you can have them on the same hardware, as I said, is basically to save the resources, to basically have a dual function system, right? And then we also have another integration, which is using sort of automated approaches, using AI for communication and communication for AI as well, let's say in terms of over-the-air computing or some other solutions. Right? So the idea is that we want to leverage the benefits of both the technologies over each other, right? So to really benefit, from each of the terms that we have seen here. And the third one would be the ubiquitous connectivity. So basically getting the connectivity anytime, anywhere, anything sort of. Right? So using non-terrestrial networks, let's say. So if you want to have direct access from a satellite in your smartphone, you can actually do that for multiple sort of applications. Or you want to, get access from, let's say, flying platforms and so on. Any sort of labs, maps, you can do that. That comes all under this ubiquitous connectivity sort of enhanced. And we can come up with several of the sort of, visions, requirements, user scenarios, and so on. Like in smart healthcare, in robotics, in blockchain technology, massive IoT, and smart homes, smart factories, indoor environment, outdoor environments, and many things that we can think of. So some of these we have tried to show in the sort of graph as well. Basically, depending on what was discussed in the sort of standards meetings and IT bar when it comes to 6G technology. So this was about the 6G framework we have, but how about we're involving the standards, right? So how about the standards? As you can see here that we had some very basic sort of standardizations when we actually started with our mobile phones, right? So we were playing around with just some, analog signaling that we moved on to digital signaling and sort of hybrid signaling. The 3G, 3G standards came in, and then you had basically, the 4G, 4G and so on, high speed, very good internet, and sort of several advanced sort of things came in, as you can also see in one of the charts that we have shown here about the wireless evolution. So the idea is that when you have the consensus about the technologies, what you're going to do, 5.5G or 6G, and even beyond, you also need to freeze the standards about it. So once you freeze the standards, it depends that how many years you take after that, but once you freeze the standards, you are going to work on those technologies. It means that is going to come in your 6G. Right? So if you hear anyone saying that in 2030 you will get 6G and so on, basically that may not be true, right? Because the idea in 2030 is that you want to freeze all these standards so that you can work, let's say, on 1 or 2 years so that you can get these technologies in the mobile. So that's very important. Right? And we see that in some latest releases. So let's say release 17, it will pick up. So we had the into production for non-trusted networks as well, right? This is very good technology. I'm not going to touch on that, even though my group works quite a bit on non-trusted networks, but it's not a new technology, right? It has been discussed, since 1990 that we were also saying that, let's involve all the, sort of non-trusted entities and connect with our environment and with our ground users and so on. So it's not new, but it has come into play again. So that's one of the important. And also the idea is that we do not want to replace our current infrastructure. We want to complement this with non-trusted. We want to have integration of our trusted network with the non-trusted network. Another important one. Then you have some other additions. So you have, definitely since 2015, 16, machine learning, AI, network slicing, and how to manage or orchestrate the network that we have. And you have edge computing, cloud computing. So let's say if you have some computationally inefficient methods or technologies, you can store them into your cloud network. And the ones that you want to actually use, you can have them on the edge plane and so on. So really depending on how you want to play around with the technologies, all these were included in release 7. So that has been wrapped up by. Then the work is going on release 18. So release 18 also includes several of these new technologies I will discuss in the next slide. And release 19 as well. So we have also decided already the early study items and system aspects on release 19 as well, right? But this is to tell you that the ideas that we project in 16 framework, they're also included in the standard. So let's look quick at the release 18 and 19. So let's say release 18, again, we are continuing with non-trusted networks. We want to explore these messy MIMO technologies, next generation MIMO techniques, holographic MIMO could be also one of the options, right? It's a fancy technology with a lot of constraints, but we are thinking about it. And basically, you can also come out with, in release 19, if you say, is basically some of the additions are there, some of the new things have come across, right? So you do your immersive communication, your XR, your extended reality, and virtual reality, those sort of things. And you want to play around with very good computing sort of solutions, that's there. Then you also want to have high mobility scenarios, either in terms of the automated vehicles, right? You want to sense all the environment around it, or you want to provide them more, how do you say that, more automation sort of based, sort of benefits. And at the same time, you also want to use your AI, machine learning, these approaches, right? You want to train your models in a way that they provide the highest accuracy possible with as low complexity as possible, which is also quite important. And you want to explore, open radio access network, and different sort of RAN technologies and so on for different applications. So that is there as well, release 19. And you have non-trusted networks as well, which we are continuing. Very important point is energy efficiency. So if you had look at the, initial 5G-based mobile devices, 5G-based communication equipments, they were not very cost efficient. So let's say 2019, 2020, so they were not so cost efficient. Huawei or some other companies, they really raised this issue that we have to make this cost efficient and energy efficient as well. So we are throwing in this massive connectivity, massive IoT, but this becomes quite important that our technologies are energy efficient as well. So this is also one of the goals that we actually have in release 19. Then we have very good addition. I mean, to be honest, it's one of the best additions that I can think of, is also doing the multifunctionality. So we are somewhere at the initial stage, so we want to co-design the sensing and communication. So we have just two early sort of study aspects. So you have communication assisted sensing. So let's say if you have your sensing equipment and communication just assisting that. Let's say your radar sensor and you want to, detect a plane going in the sky. So you're sensing that, about the plane, right? The location of trajectory or whatever you want. And you're passing that information to some sort of communication unit, right? Maybe any base station or something, whatever, is there to require that information. Or you can have sensing assisted communication. I can have my mobile device, right? I can equip this with a sensor. And if I'm walking, so maybe I don't want to have a look around, and it is going to sense for me around the, sort of monitor the environment for me and tell me what is happening. Or let's say you have the vehicular communication, let's say you have your automated car and it wants to sense around, right? Where are the traffic lights, where are the other vehicles, where are the driverless car, or so on, right? So the idea is that you can have your main device, main equipment as sensing and communication just complementing that. Or you can have your main communication device and sensing just complementing that. So depending on what your application is, we have come across some early sort of study items, right, included in 3GPP release 19. But here in academia, we can be a bit different in our course. We are saying also that why don't we play around with tunability? Why don't we try to see, where I give the dominance, that performance gets better. right? So why don't I play around more with the tunability factor? So here, because we academics, we can play around with some approximation, so we can take this liberty. But when it comes to practical systems, you can see that these are some of the feasible sort of options that you can see. And around this, you have 32 industry use cases to be precise that are included in this, smart healthcare, robotics, or augmented human sense, or different other sort of use cases you can think. So industry is working around this area. So just 2 days ago, I was in a podcast with another guy from Huawei. So he's leading the Unix Center and the ISEC group. So basically, we were discussing on these ideas as well. Then we published by Chrome. So if you're interested, we talk about the industry aspects as well on ISEC technology mainly. At the same time, when we talk about the 6G framework, the standards, and which technologies are important, we need to remember what resources we have available in that. So spectrum, as you see, is a very limited resource that we have, right? Depending on your country, which region you come from, your governments have different policies and so on spectrum. But there seems to be some sort of consensus going on. This is on which frequencies we can base our 6G services on. So we are considering mid to low to mid band, let me say, low to mid band spectrum, which is basically your centimeter wave frequencies, right? Because currently, in most of the countries, we are using sub 6 gigahertz frequencies, microwave spectrum. In many countries, maybe it's still good to keep that. So we don't have to really, put additional burden, additional overhead with trying to use different frequencies and so on. But generally, that looks like the trend that we are going to use centimeter wave band. So somewhere from, let's say, 7 gigahertz, 8 gigahertz, and so on. And the idea here is to not change too much from our current infrastructure, right? Not change too many things. So again, the same idea of, when we were doing 5G, 5.5G, and overall idea. So we want to keep similar frequency to what we already know, what we are familiar with, right? So we want to stick close to sub 6 gigahertz frequency, so 7, 8, 9, 10, 11. And the idea is they do not want to go even too much close to millimeter wave as well. Even though you see that millimeter wave was a very good candidate in 5G and 5.5G, so very good commercial applications also to Apple and many companies were trying to explore some licensed bands, unlicensed bands, and so on, using millimeter wave as well. But you have some problems with sparsity effects, your blockage effects, your high path loss as well. You cannot cover very large distances and so on. The main idea of using millimeter wave was that we have the availability of spectrum, so that we can adjust our current spectrum usage. That was the idea, but we have some sort of comms as well with higher frequencies. So let's say if a millimeter wave beam is passing through here, and if I kind of shake my hand here, so the beam is distorted. It's not very good, right? It's quite distorted. So we have this problem. So the idea is that we stick somewhere about 14 gigahertz max. We don't go further, right? But that doesn't stop us from exploring even higher frequencies. So just in some geographical locations, we might be able to use the sub-terahertz as well, right? So a lot of industries are pushing sub-terahertz too. So this could be maybe a thing of 6G beyond, right? Beyond 6G. So the idea of using sub-terahertz is that we are going to use it only in few geographical locations, not everywhere. So centimeter wave would be more of a key enabling spectrum, and sub-terahertz would be more of a complementary spectrum where we actually require very high data rates, very high speed, high capacity, and so on. We might be able to use sub-terahertz as well. And related to ISAC, because the talk is about ISAC. So if you see, there are many applications already existing on these devices. So if I want to talk about radar sensors, so you have for maritime security, air traffic control, weather monitoring, and so on. They're already using about 7 to 8 gigahertz sort of frequency radar. And if you even want to talk about the sort of sub-terahertz bands, so about 77, 78, 80 gigahertz sort of spectrum, you're using for automatic radar applications already. So it is not that difficult to combine the sensing and communication together to explore on these frequencies. But we need to remember that are these deployable? So if you are moving quite a lot with the technologies and so on, are these really deployable at this frequency? That's a key question. And we have done one paper as well very recently with NYU and NTT guys in Japan, NYU in the US. So they are kind of experts in frequency bands and so on, with Ted Rappaport and some other guys. So we also explore some experimentation work as well. So if you're interested, I would really strongly suggest to go through this particular paper if you're interested in some experimentation about some of these frequency bands and combining with ISAC as well. And you can deploy many technologies on this branch, right? From sending to wave, even terahertz, it doesn't stop us, from doing theoretical analysis and so on. So you can see that you can use it for V2V communication, I don't know, some sort of live streaming, let's say on a massive IoT scale, if you have stadium to serve and so on. You can try to use high frequencies, basically achieve the terabits per second capable speeds and so on. You can try to explore massive MIMO technologies, whatever you like, whatever fancy you can come up with. And different applications, smart home, indoor environments, outdoor environments, smart factory, robotics, many things, combined together. We also try to present some results with ISAC, sort of thing with different frequencies as well. So I would suggest if you're interested to go through this paper, please. So, just getting into the topic exactly. So sensing and communications, I don't know how much time I have. Do I have another 15, 20 minutes? 10 minutes? Okay. I will try to wrap up quick then. So as I mentioned, the fundamental principle is that basically to use two different operations that we were using separately until some point to really combine them together, right? So either on the same hardware or coexisting under one network, depending really on the application, and also trying to use the same sort of spectrum, and you can combine this with many different technologies. You can use them on sub-terahertz, terahertz band, centimeter wave, millimeter wave as well, if you want to use it, and holographic radios of applications and so on. So several of these are sort of listed here. And we are also, working quite actively on this technology. So I'm also, editing a book which is coming out very soon in a couple of weeks. It's on ISAC, so we consider different channel modeling aspects. So this is also very important point here. Waveform designs and how to improve both the performance of both these operations. Trying to provide a balance sort of thing. So trying to play around with the tunability factor and exploring with terahertz bands as well, and then trying to. I can't remember all the chapters, but we have about like 17, 18 chapters. We also try to put in some sort of standards. And we also did a paper very recently. So if you would like to have a look, so we also try to provide some standards updates and how we can use it, let's say, ISAC for robotics or for different use cases and so on, because robotics is a niche area, so we need to explore quite a bit when it comes to 6G for robotics. So several of these things we have listed some evolution of ISAC and so on. So if you're interested, I've mentioned a couple of papers here, and maybe we'll be provided with some slides as well later. Here for this talk, I wanted to discuss two very quick sort of use cases, or how you want to call it, case studies, let's say. So the idea of ISAC is already to be adjusting, the usage of spectrum that we have. At the same time, you want to also save the cost, right? Because you're trying to use the same hardware. But can I make it even more cost efficient? So let's say energy efficiency is one aspect of cost efficiency. So can I make it even more energy efficient? So I'm trying to project this idea very quickly because I don't have much time. So let's say if I try to use some sort of hybrid beamforming, right? So I'm trying to use my analog precoder and my digital conventional precoder, right? So basically, generally what you do is you use conventional beamforming. So in that case, let's say if you have 64 number of antenna, for example, you are going to use 64 RF chains and 64 quantization. But when you use the hybrid beamforming, you can reduce this number of RF chains. If you go to your manufacturer, the FPGA guy, it will give you, let's say, 32 RF chains, for example. But can I also reduce this number of RF chains? Can I optimize this? That's the point, right? So can I play around with this system architecture and come out with more energy efficient techniques? Provided that my signal is not just communication signal, it's a dual function signal, right? It has both the information of the radar sensor and also the communication information as well, right? The one that I'm trying to communicate with the user or whatever. So here the idea is, can I optimize the number of bits I have for my quantizer and the number of RF chains? I don't want to use 32 RF chains. I want to use, let's say, 4, 5, 3, whatever is the number that comes to one of the algorithms that I would plug in. So I plug in one selection method. I have a switching metric here, right? So basically, the number of RF chains, the optimized RF chains, it returns to me this method. Those number of RF chains, those number of switches are active, they're on. All the rest are off. That's basically the idea. Right? So depends on how intelligent I am with my selection method. I can have optimize, beta location for my DACs, my quantizer, and also optimize number of RF chains as well. So I might be using, let's say, 3 bits for each quantizer, or I want to use 2 bits for one quantizer, 3 bits for another quantizer, 4 bits for another, and for RF chains, I want to use 3, 4, 5, depending on which realization I'm trying. which step I'm at. So the idea is that I want to come up with a very good framework, very good selection method that helps me to do that, right? So this one, let's say if you come up with, I don't know if I have a problem very quick. So just to show you mathematically, so again, not too many details I want to show that if you have, let's say, an energy efficiency metric, you have your rate over power, right? That's basically the definition of energy efficiency. So you want to maximize that energy efficiency. If you look at the very top, it depends on the beamformers. Why it depends on beamformers? Because the dimensions of beamformers are deciding how many RF chains I'm going to do, right? So let's say my analog beamformer, it will have the dimensions of antennas, as rows, and let's say the number of RF chains as the columns, right? Again, too technical I'm going, but the idea is that selecting the beamformers will give you the optimized number of RF chains. And there's a factor of delta as well, which is basically giving you the bit allocation, how you want to optimize that. And depending on several, sensing constraints and sort of power budget constraints and so on. And idea is that you have all this mutual information. You're also trying to combine the mutual information of the sensing side and mutual information of the communication side, and you give a weighting factor. So when the weighting factor is quite high, your communication operation is in dominance. When weighting factor is quite low, your sensing performance should be in dominance, right? So you can see also, when I will show you the results, you can also see this trade-off. And the idea is that you want to use some sort of fractional programming method to make this, numerator-denominator problem into easier to solve optimization. You have difference-based optimization. So if you're working on optimization, you will know what I'm talking about. And then hybrid beamformer as well, you can use some sort of alternating minimization approach to solve this, right? And basically, in terms of the results, if I show, so here you can see that the green guy, let's say my proposed framework, and the performance starts reducing. So let's say if my energy efficiency is the performance starts reducing, right? Because the sensing part starts getting into dominance, right? That's why there is a trade-off. But when you look at the sensing performance, as low as I go in my weighting factor, my sensing guy is in dominance. My sensing performance is quite close to the ideal. So the idea I want to pitch here is that there is always a trade-off. So you can always tune in your weighting factor or your sort of dominance of both these operations, and you can play around with whether you want communication performance very good or sensing performance very good. So this is a very basic result, right? This is beam pattern. So now we are playing with probability of detection, fast around probability, average PAPR values, different waveform design techniques and so on. But this is one of the early works I wanted to show to you. And you can also come up with some sort of spectrally efficient technique. So basically, one addition that you can do in your approach is that you have some sort of interference, right? So you can also introduce some sort of interference in your program, because you will have some sort of interoperation interference, where sensing is going to interfere with communication. Your communication operation is going to interfere with your sensing part. So again, you run some sort of maximization approach where you want to maximize the mutual information, but taking into account the sort of interference that is coming from each operation over the other. I mean, because we don't have much time, so I will go further, but again, you can also explore the trade-off that we have between both these performance, right? And you can come up with different use cases. So these were, you can make them energy efficient, you can make them spectrally efficient, and you can have different use cases as well, right? So you can use them in smart healthcare or some sort of applications where you require 3D localization, where you really require the highest accuracy possible, the centimeter level sort of accuracy. So you can use your sensing capability. You can use it for robotics, right? Your AGVs and so on, or two different robots communicating with each other, right? Or let's say one robotic arm needs to sense around it, right? Because if you look at some of Huawei's prototypes, I go to a lot of conferences, so they always come up with something, combined sensing and communication together, where robotic arm can sense if there is an apple around, this banana around, and then they pick it up and give the perception, right? So the idea is that you can use ISAT, you can add enhanced sensing capabilities to your current infrastructure, current system for multiple applications, right? You can also come up with, some sort of augmented human sense. There can be also a chip underneath you, and it is able to sense something that you require it to do, for example, right? You can have some sort of gesture recognition, emotion recognition, fall detection, intrusion detection, and some sort of attacking jamming that you can also do using enhanced sort of sensing capabilities. So multiple applications you can think of. Again, we have done some papers around this as well. I'm not going to go into details of these, but there are several challenges as well that are laying ahead of us. So basically, channel modeling is one of the very important aspects. If you go to the industry guide, guys and so on, because of you're using monostatic, bistatic radar or something. There's always one question that how about the channel, right? Because communication is using these some traditional electromagnetic properties to sort out this channeling. But for sensing, things change, right? Because let's say we are coming from communication background, we can tell you thousands of things about communication principles. But how about getting sensing on board, right? This is quite important. So there has to be some coordination with sensing as well. How to model the channel that is perfect for both communication and sensing. And then also cost effectiveness is very important. So you're adding two equations together. If you want to add positioning, you want to add localization, you want to add some computing sort of technologies or sort of computing sort of fundamentals, you can add. So it can become integrated sensing, communication, and localization. Sensing, communication, and computing, or whatever you like. And we also need to come up with efficient waveform designs that how we can do the dual function signal and still come up with some sort of omnidirectional approach or sort of bidirectional, multidirectional, whatever is the case, but we also need to come up with efficient waveform design methods as well. And then compliance and regulatory considerations are very important. So especially in the case of, let's say you want to have your non-trusted network entity. So let's say if you want to get a link from a satellite to direct to your smartphone, if it is a dual function signal, it becomes very important that you take care of the compliance things, your regulatory things, because one satellite can provide access to different areas, right? It can provide access to London, to Surrey, and might cover maybe some other areas as well, right? So the idea here is that you take care of the compliance and also at the same time security and privacy as well. So you're not going to sense everything that is around you, right? So there has to be some regulation, some sort of non-technical aspects. So some ethical considerations you need to consider, and how to give different spectrum allocations as well to allow this sensing, right? So because you want to, let's say, harmonize your current cellular system with non-terrestrial networks, plus using the dual function signal. So it's such a complex scenario, you require a lot of regulatory considerations as well. I hope I gave you some idea about this. And again, the data volume handling and processing, because we're using multifunction. So I will go further. So combine this with intelligent meta surfaces too. Again, I will not talk about the technology itself. It's like a simple sort of reflector. It can be like mirror-like surface on the wall as well. And you throw in your beam and it reflects the signal towards the intended direction of the user, right? It has good applications in millimeter wave and because you can set up some sort of strong no-line of sight path by keep reflecting the signal. We have done multiple papers. There is a book also coming out with my colleague Marco Di Venzo, and we are also writing a couple of things, and we did some podcasts as well with colleagues. So if you're interested, please feel free to go through these under comms of YouTube. And different variants there can be of meta surfaces, so you can have, I don't know, multiple things. So you can keep them passive, no need to amplify them. You can make them active if you amplify them. You can do combination of these hybrid. And this is very new because this is stacked intelligent meta surfaces, so something close to the principle of deep neural networking. So how to use different layers, no linear layers, and how to increase the degrees of freedom. Very important point as well there when you want to plug in these stacked intelligent methods. Increase the degrees of freedom to achieve the highest capacity possible. So we are doing a lot of tutorials around these meta surfaces as well very recently, just to give an idea. And different synergies you can combine with sensing comms, edge computing, and multiple sort of methods. And the only point here is that these are not included in any standards yet, okay? Because you have the repeaters, you have the relayers, and so on. So this is a point that I'm asked every single time: why do I need meta surfaces, right? So we can discuss it after our talk, if you like, why we actually need meta surfaces. And you can come up with different frameworks as well. You can combine index modulation, so on. So we try to, do a communication magazine paper, try to provide a framework where basically we try to say that we do not need to actually decode the information if we are using the, because it's a large surface, right? You don't need to use all the large surface. You can use just some unit cells of its life. And how we can sort of program this information so that we don't have to decode this at the receiver. So if you're interested, we combine this with index modulation. A lot of groups working on meta surfaces work on index modulation, combining with ISAC and with meta surfaces too. So please go through that. And you can combine this with ISAC. So the idea here is that as we did with the RF chains and the antenna selection, you don't need to pick all of these, the whole surface. You can pick just few of these unit cells. So this is what we try to discuss here in this particular paper, keeping in mind that you have the balance of the performance as well for sensing and communication, right? That's very important. And you can also combine this with NTN as well. So ISAC, meta surfaces, everything can be combined with NTN. So let's say we try to present here some sort of public safety scenario. So unfortunately, we had a disaster. It can be a man-made disaster as well, but unfortunately, we had in southern Turkey very recently, right? So the idea here is that when you have the communication link broken with your base station, that was the only access point that was actually serving that area all the time because of the disaster, you can send in your non-trusted entities. You can have access from your satellite. Apple is actually using emergency services, Motorola, Huawei, all of them are using direct access from your satellite, right? They are using Globalstar satellites. Apple is using 24 Globalstar LEO satellites, right? Then you have SpaceX as well, is the biggest keyword. So what I'm trying to say here is that you can use your non-terrestrial entities, provide access to that area. And that signal doesn't have to be just communication signal. It can have a dual function signal. It can be able to sense the objects that are lost in that particular disaster affected area and also relay that information back to another control center unit or base station that is actually working, right? So it sounds complex, it is complex, but this is an idea that you can manage some public safety scenarios as well using combining ISAC and your non-terrestrial network entities. And you can synergize your meta surfaces as well. So for example, if I want to mount, I don't know, on roof of my building, stationary object, I can do that. It's like a solar panel, right? Because I want to reach larger distances, especially in a case like London or let's say New York or Tokyo or something where you actually have this dense environment, right? You can use these small meta surfaces to keep reflecting the signal until you reach your intended direction of your user or your end user until you reach that point. And you can also mount these on the satellites as well. For example, one satellite is on one side of the equator, another satellite is on the other side of the equator. How can they reach? I mean, they don't have this direct line of sight path, and the distance to cover is very high. There is very large latency there, right? You can mount your meta surfaces on each of the satellites, keep reflecting your signal like a buffer, and you reach the other side of the equator. Very ambitious, very complex, but this is possible, right? With some considerations. And you can also have this on the drones as well. So you can send in your drone mounted with some meta surface, it can reflect the signal and so on. And basically, the idea is that that signal can be also dual function signal. So if you're using, I don't know, for sensing, for agricultural applications, or any sort of use cases that I mentioned at the beginning of my talk as well, is that you can use meta surfaces, and the signal that you're going to reflect can be a dual function signal based on sensing application, and you can use non-terrestrial entities as well to reach larger distances, right? Basically, when in rural areas or disaster affected areas or any areas where I don't have the connectivity with my base station or the access point that I have. So this is just a visual representation of what I. This is my last slide, I think. And basically, that's the idea. I mean, you can send in your drones, swarm of UAVs. You can have all these satellites. They can be, having very nice sort of AI-based methods for intelligent resource allocation. You can have edge cloud computing combined together. Some information on the edge, the satellite links on the edge, and some information can be stored on the cloud as well, which is computationally inefficient or something that I don't require right away. And you can also have some coordination between the flying platforms, let's say HAPS and the LEO satellites and so on. Or you can have mega constellation NPN as well. So basically, you can have your LEO satellites coordinating with LEO satellites or NEO satellites. So you can be really ambitious as much as you want. These are complex scenarios, but it needs to be thought through in 6G that how to combine all these technologies together. So 6G will not be a standalone project, right? It will be a combination of multiple things together, working together, right? If you want to come up with a advanced project. So this is one example of that in public safety sort of. So if you would like to discuss more about this, I can discuss more details about it. But this is just sort of a visual representation of what I'm talking about, is how to combine all these technologies together, right? And then you can also enhance this with quantum sort of DRL methods like deep reinforcement learning and playing around with some quantum methods and so on. So this is a very recent paper that we have done. So to come out with a cost-efficient approach and also trying to reduce the complexity as well, based with quantum and machine learning based methods. Right? And this is using for the military sort of scenario where you're using meta surfaces plus ISAC together, ISAC signaling, and you're trying to use different sort of approaches that will reduce your complexity and the cost that you have here. So again, I would suggest if you're really interested in this paper that we published recently in JSTAC, so I think it's just in press now. We published very soon, it's accepted already. And we also do a lot of podcasts, so I would also suggest that I'm, because associated with ComSoc, quite actively. So We have a series of podcasts as well. So we discuss about all these technologies I mentioned. And we bring on, several experts from all around the world. As you can see here as well in some of these. And three more, podcasts are coming that we recorded, just a few days ago in Valencia in Spain. And we discussed with all the industry guys and the people who are actually leading this technology. Right? Because academic point of view, I can give you a lot, but we need to hear from the industry guys as well. So quite important. So just conclusions very quick. Again, I'm not going to these. ISAC has wonderful future, and it is not a new technology. It has been existing like a decade ago, but we are trying to use this for 6G now. So it has been included in the frameworks, it has been included in the standards, and you can see that how many technologies, use cases, and how many requirements, visions, and many things that we can come up with when we're trying to do sensing and communication together, right? So with this, I would say thank you, and if you have any questions, we can chat after the talk, or now you can ask. Up to you. I don't know how much time we have, but thank you so much for this. Thank you.
Thank you. An interesting